Welcome to this introduction video for the Practical and Design project presented as part of the Control Systems 354 module. This video will introduce the lab setup to be used during the DC motor control practical sessions and explain the purpose and workings of the equipment used. For further detail, as well as instructions for setting up the equipment, please consult the documents on the project background and PLC operating instructions. Let us start with the basic feedback system, as presented by this block diagram. The feedback system consists of three separate transfer functions. That of the plant, representing the physical system which behavior we want to control, the controller, which embodies our control logic, and the sensor, which extracts the information from the plant which we require to perform the control. The system is subjected to a reference input signal R. We would like the behavior of the plant to follow this reference as closely as possible. The sensor supplies us with an output signal Y, representing the current state of the plant's behavior. The difference of the reference input signal and that of the current output signal gives us the error signal E. In other words, signal E represents the difference between the current plant behavior and what we desire it to be. The error signal is applied as input to our controller. The output from our controller is the control signal U, which is formulated with the aim of rectifying the error perceived in the plant behavior. The control signal then directly affects the behavior of our plant, which is of course represented by the output signal Y. Now, let us map these system transfer functions and signals to the hardware that we're going to use. The plant consists of two main parts, the load, which is simulated by a steel disc, and the motor assembly, which includes a DC motor and a connected gearbox. The controller is implemented in several lines of computer code. The code resides and is executed on a programmable logic controller, or PLC. A PLC is a standalone computer, but we can access its control logic from a special interface program installed on the desktop PC. When the PLC executes the control logic, it receives and sends signals to the other system components through multiple input and output connections. Included in the motor assembly, between the motor and the gearbox, is an encoder. The encoder can provide real-time data regarding the rotation of the motor shaft. We can now add some more detail to our basic feedback system block diagram. We recognize that, except for the load, our plant and sensor transfer functions are physically located in the DC motor assembly. The controller transfer function resides on the PLC. Also, since the reference input signal and the sensor signal are connected as inputs, the PLC is capable of calculating the error signal. At this point, it is necessary to consider the practical implications of transmitting signals between system components. There are two signal connections which pose practical issues that must be resolved. The first case is the connection of the control signal from the PLC to the DC motor. The PLC has a 24-volt digital output. This means that the output signal can only be 0 volt or 24 volt, no values in between. The PLC can only output a small amount of current, not enough to drive the motor. The DC motor runs on a plus-minus 12 volt analog voltage. Analog meaning the input signal can be varied between the plus-minus 12 volt range. How do we make the connection? We require a motor driver, which must be connected to the lab bench power supply. We supply the motor driver with a pulse width modulation, or PWM, signal from the PLC. The PWM method allows us to make a digital signal appear as an analog signal by switching between 0 and 24 volt at a very high frequency. The motor driver then scales the signal from the bench power supply according to the PLC's PWM signal and feeds it to the motor. The bench power supply is then actually driving the motor, and it can supply enough current to meet the motor's requirements. The other case is the connection of the encoder signal to the PLC. The encoder outputs a 12-volt digital signal, in other words, either 0 or 12 volt. The PLC has a digital input available, but it works with 24 volt. To connect the encoder to the PLC, we just need to add an amplifier circuit to amplify the 12 volt signal to 24 volt. Both the motor driver and the amplifier circuit are housed inside the signal conditioning box showed in the picture. The various connections between the box and the PLC, motor and encoder are also visible. The signal conditioning functions are now also added to the block diagram. It is shown that the conversion of the control signal to a PWM signal is done on the PLC, as well as the counting of the received encoder pulses. The signal conditioning box is added to our diagram, containing the motor driver and the amplifier. The block diagram representing the practical setup is now complete. Now let us see how we can supply the system with inputs and obtain some system outputs. As mentioned earlier, the PLC is a standalone controller, but it can be accessed through the desktop PC through a special interface program named TIA Portal. The TIA Portal program is used to write the code of our control programs and download it to the PLC, so that the PLC can execute it. The program also displays the values of variables within the PLC during operation and allows us to make changes to parameters to which the PLC will then react. The display of variable and parameter values is done via a watch table in the TIA Portal. The watch table can be opened from the project tree window on the left-hand side. The watch table displays a list of all the system variables and parameters. These values can be modified from this table. In this list, the variable representing the reference input signal will appear. Then, by modifying that variable and updating the PLC, we in fact supply the system with an input. The block diagram now shows that we can access the control loop program in the PLC and supply an input signal from the TIA Portal program. As mentioned before, the TIA Portal displays the real-time values of our system variables, but we want to measure these variables as outputs. The practical setup is equipped with an oscilloscope, which is wired to measure two output channels of the PLC. The oscilloscope is connected to the desktop PC via the USB port. This connection, together with a special program called Picoscope, allows the measured signals of the oscilloscope to be displayed and saved on the PC. This image shows a sample measurement obtained from the oscilloscope using the Picoscope program. The measurement shows two signals, designated in blue and red. If we were to measure the reference input signal and the encoder output signal with the oscilloscope, the block diagram will look as follows.